Hi, and welcome to our presentation on the NP-completeness of tokenization. I'm Philip, and this is joint work with Gregor and Tiago. So, while at this workshop probably all agree that tokenization is an interesting thing to study, let me still use this as a hook to pose a concrete research question. And the purpose of tokenization is that we want to convert our data, our input, so that we can properly use it as the input for large language models. And what this concretely means is that you're given raw linguistic data and want to split it into sensible linguistic units and assign numbers to these so that you create a vector space on which the LLM can operate. If you choose a good tokenizer, that means your training will be far more efficient, and as compute is still somehow a limiting factor, this will increase your model performance. On the other hand, if you have a bad tokenizer, you can actually run into problems, and things that you might want to learn will take much longer to learn. So this is just the key point why we're tokenizing. It will actually make our models better if we have a good tokenizer. So why don't we just create tokenizers with that in mind? Well, the problem is model performance is not really a tangible metric. You can't really measure it because you need to actually train the model to find out how good your tokenization is in that case. And you cannot even be sure that it's not just down to the parameters that you've chosen. Also, because we don't really understand LLMs that well, we can't also give any theoretical guarantees on the model performance just from tokenization. What this means is that we have to make do with proxy objectives. And there are many, and in this work we will focus on compression as it is the most popular. So let me define the variants of tokenization that we'll be looking at. The first one we coin bottom-up tokenization, and it's a formalization of what happens in BPE. And so here you are given a set of merges and additionally an input that you want to tokenize. The first step that you do is quite independent of the tokenizer, is that you do pre-tokenization. And then what you do for bottom-up tokenization is you start at the bottom, so at the character level, or generally usually at the byte level. And then you iteratively apply merges in the order that you are given them. So the first merge that we have here is H and E. So we apply this merge whenever we have these tokens next to each other. In that order, we will merge them. Then you see the token or the merge RE. We will also merge these. These also appear twice in the string. And now you can also merge tokens that you have seen before. And here it's really important that you do it in the order that you are given, because only now the token HE exists. And you can merge the tokens T and HE to get THE. And this implicitly also creates a set of tokens, these being the character tokens that you get in the beginning, and also a token for each merge. And now the question is, what merges should you choose and what resulting tokens should you get? And what BPE does is just in every step chooses greedily the tokens that the merge that now gives the best compression in the next step. But it's not hard to construct examples where this would not be the best thing to do. Another thing that you can observe here, that in this final tokenization, the token HE does not appear at all. This is due to the fact that we need it for the merge to happen, but in the end there's another merge happening that will always subsume this token. And this leads us to also look at another model of tokenization. This is what we call direct tokenization, and here's really the idea that you want to maximize the compression with any suitable set of tokens. So again, you are given now directly just a set of tokens. You're given a string, you pre-tokenize it, and then you apply these tokens in a way that your data cells then results in the shortest number of tokens possible. Also here I want to point out that just applying these tokens greedily might not be the best way to do it. But luckily for us, Schmidt et al. Have shown with the path piece algorithm that you can efficiently compute this compression maximal application. So, and here you can see once you're given the set of tokens, you can efficiently also apply them. But again, the question is, what tokens should you choose? And this is really what we study here. Let me formalize the problem again with the example of the direct tokenization problem. So you are given a string and a set of tokens, and then you optimally apply these tokens on this string. And then what the problem is actually is to find a set of tokens such that the entire data set is reduced to a size of at most delta, and you have to include all the characters and are given at most k additional tokens that you can choose. And in the paper we have a similar definition for bottom up, which is just a bit more complicated because it has the formalized merges, but you can find it nonetheless. And while these definitions might be a handful, our result is now very easy to state. Both the direct and bottom-up problems are NP-complete to solve. Now, for the people that are interested in the technical ideas behind this, I want to give one slide on the reduction, but if you're not interested, don't worry. On the next slide, we'll get to discussing the implications of this. Our reduction starts at the max 2 set problem. We're given a set of variables, a set of clauses, each clause consisting of 2 literals. The literals, of course, coming from the variables, just being positive or negative. And this would just be 2 set, and this is a problem that's efficiently solvable. So what we also include is a target gamma. And now the question becomes whether you can satisfy gamma clauses, and how can you satisfy clauses? Of course, by assigning true or false to the corresponding variables and then seeing how the clauses evaluate. So this is a very nice NP-complete problem. Now let's see what we reduce to, and I'll again stick to the example of direct tokenization as it is a bit simpler. So now we're given as input an alphabet, and for each variable we'll introduce 2 characters corresponding to true and false for the variables, and just some additional character. Now the dataset will consist of 1 string for each clause, where the variables in their positive or negative form, as they appear in the clause, will now appear in this string of length 5, separated by this special character. And we also include more strings that are given this dataset D prime. I will explain later what these do. Now for the targets here, we are given a vocab size k, which we set to j. So we are allowed as many tokens as we have variables. And we have a target delta, so that's the size that we want to compress to. And the important part that I want to point out here is this -2 gamma. So basically for every clause that we want to satisfy, we have to save another 2 tokens somewhere, and it will be in the dataset D. So now again the objective is, can we compress this entire dataset to delta submills with at most k different tokens? And we do this by choosing tokens. And here I want to be more precise, and this is what D prime does is, you have to choose between these 2 tokens here. And these correspond to setting xj to true or to false. And what this means is, if you choose the token that corresponds to true, this means you set the corresponding variable to true. And then this clause is satisfied, and you can see that in the dataset corresponding to the clause, this 3 gram will appear, so you can reduce this string from length 5 to length 3, giving you exactly the saving of 2 that we described earlier. And the main technical part is really in this D prime, where you want to enforce that these are really the tokens that you have to choose. Also, I want to say that for bottom-up tokenization, the proof is very similar, actually. It's a bit more complicated, especially this set D prime gets a lot larger, but in the end we want basically to make merges that get to these same tokens. But just because they're merges, then you need to do a little bit more work. So let's get to the implications that this result has. The main takeaway that we want you to have is you cannot find the best tokenizer in terms of compression, but that doesn't mean you can't find a good one. You can very much still find a good one. And so, for example, algorithms as BPE are the way to go. They're approximation algorithms. However, you can think about how to find perhaps better approximation algorithms for compression. And one avenue that we currently think is a bit underexplored is the connection to the actual field of compression. Because BPE did originate roughly 30 years ago as a compression algorithm in the field of grammar-based compression, but was not too successful there. So we think exploring this connection deeper might yield valuable insight into how we can compress for tokenization. Now I want to finish on a few open questions. The first one being, quite obviously, which efficient tokenizer achieves the best compression. Also, in a similar vein, we don't want to tokenize every possible dataset. We want to tokenize natural language, and maybe there are certain properties of natural language that make tokenization easier. This is also an interesting thing to study. The most general question that we are certainly not the first to state is, what should the auxiliary objective be? We have only looked at compression here, but as I said in the beginning, there are others that are very reasonable. And now this NP-completeness result is perhaps some argument that you should not look at compression, because if there's another objective that is efficiently computable, that would be a strong argument to use it, if it's also a good indicator of model performance. For that reason, you should also study for these other objectives whether tokenization still is NP-complete or not efficiently solvable. And then, of course, we can finish by saying, if you then know what the objective really should be, more or less, then the question is, what is the best algorithm for this objective? So to summarize, tokenization appears to be an inherently approximate field. Maximizing for compression at least is NP-complete. And now the challenge is to understand which proxy objectives truly matter and how closely we can approximate them in practice. This is all that I wanted to tell you today. I hope you found it interesting, and thank you for listening.